We tend to think of magnets as these constant, unwavering forces, right? But what if I told you every single one is a secret weakness, a breaking point where its power just, poof, vanishes? Today, we're going to dive into what that is and exactly how to trigger it. So, here's the big question. Can you really destroy a magnet's power with just a little bit of heat? I mean, think about it. Could this incredible, invisible force really be that fragile? Well, the answer is a huge yes. But here's the catch. It's not like it just slowly fades away. Nope. There's this one specific critical tipping point where a magnet's power just disappears instantly. So, let's break down exactly how that works. Okay, so here's what we've got on tap. First, we'll look at a magnet's secret weakness. Then, we're going to get microscopic and meet the army of atoms behind the magic. After that, we'll pinpoint the breaking point, figure out how to predict the chaos with a really cool law, and finally, we'll see why any of this actually matters out there in the real world. All right, first up, a magnet's secret weakness. And you can really think of this as a story. It's this epic battle going on inside the magnet, a constant struggle between perfect, structured order and the total chaos that energy brings to the party. And that chaotic force? It's just temperature. It's that simple. Every single permanent magnet, I don't care how strong it is, has this one vulnerability. See, when you add heat, you're basically just pumping in chaotic energy. It shakes everything up on the inside and threatens the very thing that makes it a magnet in the first place. So, to really get how this works, we've got to zoom way, way in, all the way down to the atomic level. This is where we meet the two main states of magnetism, ferromagnetism and paramagnetism. And honestly, the difference between them is kind of like the difference between a perfectly disciplined army and a totally chaotic crowd. So, check this out. On one side, you've got ferromagnetism. Inside these materials, all the tiny little magnetic bits, or domains, are lined up perfectly, just like soldiers in formation. That's what gives you that strong, constant pull you feel from a fridge magnet. But then, on the other side, you have paramagnetism. Here, all those little atomic magnets are just pointing every which way. Total chaos, like a crowd of people. They might still be weakly drawn to a different magnet, but on their own, they have no unified power whatsoever. And that right there brings us to the heart of the mystery. What's the trigger? What can take that powerful, disciplined army of atoms and just turn it into a disorganized, powerless crowd in an instant? What causes that complete breakdown of order? Well, the answer is what we're talking about next, the breaking point. This is where we get to the single most important idea for understanding this whole thing. It's a very specific threshold, and it's called the Curie temperature. Okay, so the Curie temperature, or TC for short, think of it as the ultimate point of no return. The second you heat a ferromagnetic material up to this exact temperature, that internal army we talked about just falls apart. It instantly loses its permanent magnetism and flips over to being paramagnetic. And I want to stress this, it's not a slow fade. It's a sudden, dramatic switch. But here's the really wild part. This switch from order to chaos, it's not random at all. It's totally predictable. And that brings us to the math behind the magic. Predicting the chaos with something called the Curie-Weiss Law. This is the equation that tells us exactly what's going on as a material gets closer and closer to its breaking point. Now, before I throw an equation at you, we need to know what we're even measuring. The key ingredient here is something called magnetic susceptibility. It's represented by that Greek letter, chi. But really, all it is a number that tells you how easily something can become magnetic. If it has a high susceptibility, it's super eager to get magnetized by a nearby field. And here it is, the Curie-Weiss Law. Now, don't worry about memorizing it, just look at the relationship. T is the temperature right now, and Tc is that special Curie temperature, the breaking point. So, what happens when T gets really, really close to Tc? Well, that number on the bottom of the fraction gets super tiny, right? And what happens when you divide by a really, really small number? The result just explodes. The magnetic susceptibility, chi, just skyrockets, theoretically heading towards infinity right at that breaking point. So a little backstory. This law came from Pierre-Ernest Weiss, who built on the work of Pierre Curie. Yep, that Curie, Marie Curie's husband. What the law does is perfectly describe how the material acts once it's above its Curie temperature. But its craziest prediction is that right at that temperature, the susceptibility goes nuts, theoretically becoming infinite. This kind of sudden, dramatic change is what scientists call a critical phenomenon. It's kind of like how water is just water right up until it hits its boiling point, and then boom, it instantly starts turning into steam. This chart really helps visualize it. Look, as the temperature climbs and gets closer and closer to that Curie point, you see the magnetic susceptibility just shoot up. It gets super, super high. But then, the very instant it crosses that line, bam, the state flips and the susceptibility completely collapses. Order becomes chaos just like that. Okay, so this is all really cool physics, but you might be thinking, so what? Why does this actually matter? Well, it turns out this magnetic breaking point is incredibly useful. This isn't just some weird thing that happens in a lab. The Curie point is a crucial part of technology we use every day, from hard drives to temperature controls. Believe it or not, we figured out how to turn this weakness into a strength. Think about magneto-optical storage. A laser heats up a tiny, tiny spot to its Curie temperature, which basically erases it by neutralizing the magnetism. Then, as it cools back down, a new magnetic field writes the new data. How cool is that? It's also used in things like temperature control systems. Imagine a magnet holding a switch closed. If the device starts to overheat and hits that Curie point, the magnet just stops working. The switch opens, the circuit breaks, and you've got a super simple, foolproof safety mechanism. So, if there's one big idea to walk away with, it's this. What seems like a destructive weakness is actually an incredible tool. The Curie-Weiss Law isn't just about describing a magnet's breaking point. It's a blueprint. It shows us that if we can control temperature with precision, we can control magnetism with precision. One of the most powerful, invisible forces in nature, and we can switch it on and off. And that just leaves me with one final question for you. We just saw how a fundamental force like magnetism can be totally flipped on its head by something as simple as heat. It really makes you wonder, right? What other invisible forces are all around us just sitting there, waiting for the right little push to change completely?